Hello everyone, thank you for attending my talk. My name is Rahil and today I'll present my work on Lorenz-like dynamical systems that arise in modeling of what we call these active wave particle entities. Alright, so let me start by introducing these active wave particle entities to you as they are realized in experiments. So back in 2005, Yves Couder and colleagues in Paris discovered that if a container filled with silicon oil is vibrated vertically, then a droplet of the same oil can be made to bounce and walk on the liquid surface. So as you see in the top slow motion videos, each time the droplet bounces, it generates a localized standing decaying wave around itself. The droplet then interacts with these waves on subsequent bounces to propel itself horizontally. So these droplets, they are called walkers and superwalkers. Now, three key things to note about this system. So the first is that the droplet and its underlying wave, they coexist as a wave particle entity. So if the droplet were to disappear, the underlying waves would decay and the liquid surface would become completely flat. Now, the second is that at high amplitudes of path vibrations, the waves generated by the droplet decay very slowly in time. So the droplet is not only affected by its most recently generated waves, but also by the waves it generated many bounces before. This gives rise to path memory in the system. And then lastly, these droplets are active in the sense of active particles and active matter. So the droplets locally extract energy from the vibrating path and convert it into directed motion. So hence we call these as active wave particle entities. Now these droplets are quite easy to produce in simple experiments. So if you'd like to make a setup yourself, you can have a look at this link on the bottom right corner. Okay, so now interestingly, in the high memory regime, so the regime where the particle generated waves decay very slowly in time, these wave particle entities, they have been shown to mimic several behaviors that are typically associated with the quantum world. So for example, if we put the droplet in a circular cavity whose dimensions are of the same order as the waves generated by the droplet, then you can see that the droplet will undergo a chaotic looking trajectory. Now, if the droplet is tracked for a few hours in experiments, and if we plot a histogram of where the droplet has been inside a cavity, then you can get a coherent wave-like structure in the probability distribution of the droplet inside the cavity. So what we are seeing is chaotic walking dynamics of the droplet inside the cavity results in the emergence of a coherent wave-like statistics. And then another example is you can get an analog of quantum tunneling if you consider a droplet confined by subsurface barriers. The droplet will typically reflect from these subsurface barriers, but then occasionally it can unpredictably cross these barriers, and you can get an analog of quantum tunneling. And then you can also have analogs of particle diffraction and interference. So if the droplet is fired at a single slit or a double slit setup, then you can get diffraction and interference patterns appearing. And then you can also have an analog of quantization, where if you confine the droplet in a harmonic potential using a ferrofluid and magnetic fields, then you'll get a discrete set of limit cycle orbits for the droplet, right? So these are some examples of different hydrodynamic quantum analogs that these active wave particle entities exhibit. Alright, so now a simplified theoretical model that captures the key walking dynamics of these wave particle entities was first derived by Oza and colleagues in 2013, and it's called the stroboscopic model. So imagine that if we only capture one image of the droplet per bounce in experiments, then the motion of these droplets would look something like as you see in this video, right? So you only see the horizontal motion, but not the vertical motion. And the stroboscopic model does exactly that. So it averages over the vertical dynamics of the particle and gives us an equation of motion for the horizontal dynamics. So here is the equation of motion we get for the wave particle entity moving in one horizontal dimension. And it's essentially an equation for the Newton's second law in dimensionless form, right? So on the left side, you have an inertia term. So you can think of kappa as a dimensionless mass. Now there is dissipation in the system. So you have a drag term proportional to velocity. And then now this complex looking term on the right hand side is the force that the droplet feels from its underlying waves. Now in the stroboscopic model, since we have averaged over the vertical dynamics, the droplet can be thought of as a continuous emitter of these waves. So at each instant, the droplet generates a waveform A of x that decays exponentially in time. And then the total wave field is calculated by integrating over the past history of all these waveforms generated. So it will give us a total overall wave field. And then the force that the particle feels will be proportional to the gradient of this overall wave field, right? And this parameter beta, in a sense, couples the strength of the force. So it's a coefficient that determines the strength of this wave memory force. So in this way, we get an integral differential equation that describes the motion of the wave particle entity in the horizontal direction. And we have these two dimensionless parameters. So kappa as a dimensionless mass and beta as a dimensionless wave memory force coefficient. Now, the experimentally observed waves generated by the droplet on each bounce, they have features of both wave oscillations and spatial decay as well. Now, if we consider a simplified picture where we capture the oscillation in the waves and ignore the spatial decay, then we can use a very simple cosine waveform for the waves generated by the droplet. And the reason for doing this is because then we can convert this complex integral differential equation into a finite set of ordinary differential equations. And it turns out that in this case, the integral differential equation maps onto the classic Lorenz system, right? So the capital X variable in the Lorenz system will be the velocity of the droplet. The capital Y variable is this wave memory force acting on the droplet, and the capital Z variable is related to the amplitude of the wave at the droplet location, and the sigma R and B of the Lorenz system are nicely related to the parameters kappa and beta of the droplet model. So you have this nice one-to-one correspondence between the droplet's equation of motion and the Lorenz system when you look at this simplified wave field. Now, the Lorenz system has different equilibrium points, and these can now be related to the dynamical features of these wave particle entity. So this is kind of like a cartoonish picture showing the bifurcations that happen in the Lorenz system as the parameter R is varied. So at very small values of R in the Lorenz system, there is only one fixed point at the origin, and this would correspond to a stationary state of the wave particle entity, since the capital X variable, which represents the velocity of the particle, is 0. Now, as R increases, one gets a pitchfork bifurcation in the Lorenz system, where the stationary state becomes unstable, and for the droplet this would then correspond to the two steady walking state, one moving to the right and another one moving to the left, right? So this is for example the right moving state, and this is how it would look like in the physical picture of the wave particle entity. And the Lorenz system, this would be a fixed point located on the positive side of the x-axis. And then in the Lorenz system, as you further increase R, you go under a sequence of complex bifurcation, and eventually one gets chaos, right? And then this chaotic state where you get the Lorenz attractor would correspond to an irregular motion of the wave particle entity, where it can move between left and right moving states, right? So you can map these equilibria and dynamical features of the Lorenz system onto different types of trajectories and motion of the wave particle entity. Now, since most of these hydrodynamic quantum analogs are realized in the high memory regime, it would be useful to understand the behavior of a simple model in that limit. So to do this neatly, we can non-dimensionalize the original integral differential equation in a different way, and we can get Lorenz-like system again with parameters appearing in different places, right? So this is what we currently have with kappa and beta as the parameters, but if we non-dimensionalize in a different way, then we end up with again a Lorenz system, but with the parameters r and tau, and these r and tau are can be mapped to kappa and beta. And the reason for doing this is because now r and tau have nice physical interpretation in the context of the wave particle entity. So you can think of r as a dimensionless wave amplitude of the wave particle entity, and then the tau is the dimensionless wave decay rate. So it can be directly linked to the memory of the system. So the larger the tau, the slowly the waves decay. So if we now take the limit of high memory in this representation of the models, which would correspond to tau going to infinity, then we find that terms further drop out in the Lorenz-like system, and we get these sets of equations, which are known as the diffusionless Lorentz system. So this system has been studied in detail by Van der Schaar and Maas. And what we can now do is we can now apply it in the context of the walking droplets to see what dynamical features give rise to what type of trajectories and behavior for the wave particle entity. So we now only have one parameter r, which is the dimensionless wave amplitude of the particle generated waves. Alright, so here is a bifurcation diagram of the system as a function of the parameter r, and the bottom panel is showing the maximum Lyapunov exponent. Now the different colors are the qualitatively different types of wave particle entity trajectory that you get. So red is a symmetric limit cycle in the phase space of the diffusionless Lorentz system, and this corresponds to a particle oscillating back and forth. So it is trapped in its own wave field and it just oscillates back and forth. Similarly, yellow is an asymmetric limit cycle. So this would again give you oscillations in the particle's trajectory, but with a net drift. And then purple is a chaotic attractor in the phase space of the diffusionless Lorentz system, and this would correspond to a chaotic walk for the WPE. Alright, so now let me just focus on one small region of this bifurcation diagram, so the region of small values of this parameter r. And in this regime, this is how the bifurcation diagram looks like. So you get this self-similar structure of bifurcations. And the three types of trajectories that we discussed, they appear in intermittent form in this regime. So the particle will stay stationary for a period and then suddenly start walking and make a quick jump. And it can do either back and forth or in the same direction, or it can do it in an irregular way. Alright, so let us try to understand physically why this intermittent motion arises. So initially, the particle tries to build up its wave field by generating small amplitude waves because r is small, and this results in the wave constructively interfering with its waves because it's not moving anywhere, so it is building up the wave field up to a point. And then the particle transitions from the stationary to a walking state once it has built up a critical amount of wave field. And once it starts walking, it moves by half a wavelength and finds itself in an adjacent minima. Now at this location of the minima, the particle will continue to generate waves, but now the new waves that the particle will generate will interfere destructively with the previously generated wave field. So then, in a sense, the droplet is erasing its wave field in this process, and it will go back to having a flat, no wave field, and then this process repeats, and hence you get this intermittent motion where you have a buildup of wave field where the particle is stationary, and then it suddenly does a step of half a wavelength, and then the process repeats. Now, if we consider the irregular trajectories in the intermittent regime, and we look at the statistics of this by considering many different initial conditions, starting at the origin, but with different initial velocities, then this is how the probability distribution evolves in time. So you can see it going from A to E, right? So there is a diffusive spread in the trajectory because these particles are doing chaotic walk. But however, due to the intermittent nature of the trajectories, wave-like features persist in the probability distribution as it spreads out. All right, so in conclusion, we have active wave particle entities that materialize as walking and superwalking droplets on the free surface of vibrating liquid bath. In one dimension, a simple dynamical model of these wave particle entities gives us Lorenz-like dynamical system. And in this infinite memory limit, we get a simpler form, which is the diffusionless Lorentz system. And then we have shown that we can connect the phase space geometry and dynamics of these Lorenz-like systems to different trajectories and motion of the wave particle entity. And we saw that in the intermittent regime of the chaotic state, we have a wave-like probability distribution appearing. And then lastly, investigating these simple Lorenz-like models of these wave particle entities might allow us to rationalize the wave-like features in these statistics and how they emerge from the underlying chaotic dynamics. Thank you for listening to my talk. If you'd like to learn more, then you can have a look at our paper, which is open access, or contact me for any questions. Thank you.